Okay, welcome once again to this lecture on spectrophotometry. This is part 2. Earlier we have discussed, or I discussed with you the properties of light, and as a particle, we know that it interacts, or the particle of light or photon interacts with matter. Now the question is, how does light interact with matter? There are 5 types of interactions. They are absorption, emission, reflection, refraction, and scattering. However, in our case, since we are discussing the fundamentals or principles of spectrophotometry, we will just be discussing this type of interaction, which is absorption. Absorption happens when when the energy from a photon is transferred to an atom or a molecule, which produces a transition from a lower energy to a higher energy. Okay, absorption is represented by this diagram. So, before absorption of energy of a photon, the electron is said to be on the ground state. Alright? The ground state molecule can absorb energy and becomes excited. The electron that is the electron that absorbs energy is excited to the excited state. In this case, we have an E2. From the ground state, we have E1. The difference between E2 and E1, we call that delta E, or the change in energy. The molecule will absorb only light if the photon have the same or have the exact energy, okay, or delta E required to excite the ground state molecule. So here, in order to excite the electron from ground state to the excited state, the electron must absorb the energy from the photon. Okay, the red arrow is now in the excited state. However, this transition is very quick. As we can see in this next slide, when an electron is promoted to the higher energy level, as I said, this transition is very quick from excited state. Okay, this is the ground state, for example. After this electron absorb the energy of a photon, it will be promoted to higher energy level. Okay, that is absorption. However, as I said, the transition is very quick. In split of second, the electron from excited state goes back to the ground state again. When that happens, the light energy is emitted. The high energy photon is emitted, and this is actually measured. Okay, the emission is measured. The particle that is responsible for the absorption of light is called chromophore. Okay? Any substance that absorbs visible light appears colored when white light is transmitted through it or reflected from it. So white light contains all the colors in the visible spectrum. Remember, the visible spectrum, this constitute the primary color, the red, orange, yellow. And remember that in the entire electromagnetic spectrum, this visible spectrum is only the tiny fraction of the entire electromagnetic spectrum. The observed color is the complement of the absorbed color. Okay? Now, this symbol, lambda max, or remember lambda is the wavelength. Okay? The lambda max represents the wavelength absorbed by the sample, and thus this represents the energy gap of the transition. Remember earlier, as I said, in order to promote the electron from ground state to excited state, there must be an energy. Okay, and this energy is represented by the change or the delta E. It says here, the lambda max represents the energy gap of the transition. This is the energy gap. No? The delta E is the energy gap of the transition. And thus is a molecular property and is a characteristic of the molecular structure. The lambda max is the molecular characteristic. Okay? It's an inherent property of the molecule because every molecule, they have their own maximum wavelength of absorption, or simply known as lambda max. Okay? Now, in this table, we will see the complementary color and then the absorbed color. So when, for example, bromophenol blue has a lambda max of 591 nanometers and its observed color is blue. Okay? What do we observe? We observe blue. Okay? That is because orange color is absorbed. So for example, we see a color red. Okay? When white light is passed through that sample, okay, blue to green color is absorbed at 470 to 500 nanometers. Okay, this is the region. Okay, of course, that particular sample has a lambda max, but the absorption happens at this range of wavelength. Okay, when color blue to green is absorbed, we observe green. So it's nice if we could remember these complementary colors. When white light from a continuous source, you see you can simply source the white light from a simple bulb. Okay, it can be a incandescent bulb. Incandescent bulb, it has a a tungsten filament. If you have your motorcycle with you, you would see a filament. Okay, it's a wire made of tungsten. When the tungsten filament is heated, it glows. Okay, and it's a source of white light. Okay, white light from a continuous source is passed through a monochromator. The monochromator could be in the form of prism or diffraction grating. What monochromator does is selects, okay, a narrow band of wavelength from the incident beam. So after the white light is passed through the prism, you notice that the prism separates the uh, components of white light. White light, as I said, is composed of all of the colors. So the prism separates that. And depending on the wavelength, okay, the light will pass through the slit, okay, or an opening. And this light that passes through the slit, this is the light that will be absorbed by the sample. Okay? In a diffraction grating, when light is passed through this grating, the light separates based on bending. Okay? And the same principle, the light of the based on the desired wavelength will pass through the slit, and this light that passes through the slit is the one that will be absorbed by the sample. The passing of light through the sample can also be represented by this diagram. Okay, so the monochromatic light travels through a sample. Then the irradiance of the emergent light is measured. So in this diagram, you have the source of light, then it passes through a wavelength selector that is a monochromator, could be in the form of a prism or a diffraction grating. Then from this monochromator, the light will pass through a slit. Okay, and then the light strikes the sample. Okay, as the light strikes the sample, some of the light is absorbed. All right, and then depending on the concentration of this sample, some light would be transmitted, and the light that is transmitted is detected by the detector. This is present. This is a component. The detector is a component of the machine or the spectrophotometer. Usually, the sample, the path length of the sample is measured. Okay, in a normal spectrophotometric activities, the path length is usually measured in centimeter. It has been said earlier that the irradiance of the emergent light is measured. What is that irradiance? So remember, there's a light that passes through the slit and the light strikes the sample. Irradiance, or symbolized by P, is the energy per second per unit area of the light beam. The light beam is the light that passes through the slit that will pass through the sample. Okay, so it has an irradiance. When light is absorbed by the sample, the irradiance of the beam of light is decreased. So the light that passes through the sample has an irradiance. Okay, it has an energy, and as the light strikes the sample, the irradiance beam is decreased. Okay, so as you notice here, the irradiance of light that passes through the sample, symbolized by P sub O, becomes P because some of the energy is absorbed by the sample. We say that the beam of light is decreased. Okay, this time let us describe what is transmittance. Transmittance is defined as the fraction of the original light that passes through the sample. Remember, in this diagram, the light that emerges from the monochromator has a certain irradiance, and as the energy or as the light passes through the sample, the irradiance of the light beam decreases. Okay, and as the light passes through, the light that is transmitted is detected by the detector. So what a transmittance is, the fraction of the original light. Okay, transmittance is the ratio of the radiant power. All right, this is the P, symbolized by P because the irradiant power of P, symbolized by P, has already been decreased. Okay, Transmittance is the ratio of the radiant power in a beam of radiation after it has passed through a sample to the power of the incident beam. So the numerator is the radiant power that has been decreased, okay, and then P sub O is the original, okay, original light beam, all right, that passed through the sample. The problem with transmittance or percent transmittance is when you plot these two parameters with concentration, you would not attain um, straight standard curve, okay? Because in construction of standard calibration curve, you must produce a straight line, okay? What you produce in what you produce when you plot percent transmittance and concentration is logarithmic relationship, okay, logarithmic rather than linear. So instead of plotting the concentration of the sample versus the transmittance or percent transmittance, it is rather acceptable to plot absorbance versus transmittance. So if you are using a machine that gives or that produces a readout of percent transmittance, you need to convert the percent transmittance into absorbance, okay, and right here I have indicated the conversion or the formula how to convert percent transmittance to absorbance. Okay, absorbance can be uh, can be taken from the percent logarithmic. Okay, so you just have to practice the following. So if the percent transmittance is 100, meaning 100% of the light uh, pass through, that means zero absorbance. Okay, if 10% of the light is absorbed by the sample, then we could say that 1 is the absorbance. Absorbance is unitless, as I will see that in the coming slide. When absorbance is plotted against concentration, so you have here absorbance in the y-axis and concentration in the um, x-axis. What we produce is a straight line, and we can use this as our calibration curve. So this is the beauty of plotting absorbance versus concentration, because earlier when we plot percent transmittance with concentration, what we get is logarithmic, okay? Unlike here, we have a linear relationship. Now, this graph follows Beer's law or Beer-Lamberts law. What is Beer-Lamberts law? Okay, it says Beer-Lamberts law is a linear relationship between absorbance in the concentration of the absorbing species in the sample. Take note that we employ this in order to determine the concentration of the sample. So again, you have the light, okay, it passes through the monochromator, okay, and then depending on the wavelength that we adopt, the light passes through the sample, okay. Our objective is to determine the concentration of the analyte, okay, determine the concentration of the analyte, and that to do that, the light that passes through the sample is measured in terms of transmittance or absorbance. So our goal is to determine the concentration, okay, concentration of the analyte in your sample. So to do that, as I said, we need to construct a calibration curve. We need to construct a calibration curve. That follows, the calibration curve must follow Beer-Lamberts Law, which is the relationship between the absorbance and the concentration. Okay? Not between transmittance and concentration. So absorbance is equal to epsilon times B times C, where A is the absorbance, B is the path length. Remember, as I said, the sample is placed in a container, and usually this container is a cuvette. Okay? This cuvette has a measured dimension, usually in centimeter. Okay? So the B is the path length, and the epsilon is absorptivity or molar absorptivity, extinction coefficient. This is the inherent property of the molecule. And C is the concentration. You can use any concentration. It could be molarity, ppm, or grams per ml. But of course, when you use variable concentration, you must be able to convert one unit to another. Okay? So what is path length, or in the equation is symbolized by B? This is the distance of light travels through the measured solution. It is the inside diameter of the sample container placed in the light path. So this is the light path, okay, and this is the cell holder, okay, and usually what we put in the cell holder is a cuvette, okay, and this container is measured. The inside diameter of the sample container is measured, okay. The path length is measured in units of length, usually centimeters or millimeter. Then epsilon, or molar absorptivity, as I said earlier, is the inherent ability of the chemical species to absorb light. Okay? It's a characteristic, it's an inherent characteristic of the absorbing species itself. Okay, so remember that A, absorbance, is equal to epsilon times B, which is path length times concentration. When the concentration is in molarity, the path length is in centimeter. Thus, the unit of absorptivity must be liter per mole per centimeter. Under this specific condition, the absorptivity is called the molar absorptivity or the molar extinction coefficient. Sample problem. The measured absorbance of a solution is 0.544. So notice that this is unitless. Okay? And the path length is 1 centimeter. If the concentration is 1.4 times 10 to the negative 3 molar, what is the molar absorptivity of this analyte? So you are asked to solve for the extinction coefficient. Okay? Knowing the formula of absorbance, which is epsilon BC, absorbance is given to be 0.544. The path length, which is B, is 1 centimeter. The concentration is also given. Okay, the molar absorptivity or the molar extinction coefficient is 389 liter per mole per centimeter. Another example here is this complex iron thiocyanate has a lambda max. The wavelength of maximum absorption is 500 nanometer. It says here it has a molar absorptivity of 7.0 times 10 to the positive 3 liter per mole per centimeter. You are asked to calculate for the absorbance. Using the formula, A is equal to epsilon BC.